Hello AP Chemistry and welcome to the 16.3 and probably 16.4 auto ionization of water and the pH scale. So first of all, we talked about this last year, right, where water, to a very, very small degree, right, we can get two water molecules, right, to basically react with one another. One of them serves as a proton donor, one of them serves as the proton acceptor, and we end up with a hydroxide and a hydronium, right, to show for it, okay? Now, obviously that happens only a very, very tiny bit, which is why pure water, not very conductive, because there are very few actual ions present in pure water, right? Now, here, right, that part is really important, right? The fact that the auto-ionization of water is what leads to the presence of hydroxides or hydroniums in water, because that's what defines neutral, right? In a neutral solution where there are only water molecules present, right, then what should happen is that hydroxide and hydronium should be equal. Yes, hydroxide and hydronium should be equal, which at 25 degrees Celsius means concentrations of 1.0 times 10 to the negative 14th, right? But note that that is at 25 degrees Celsius, and just like every K expression, right, which I did not write down here, right, but we have our K expression, right, which says K is equal to, right, H plus times OH minus, right? That's our K expression, is equal to 1 times 10 to the negative 14th, and that's our KW, right? Now, that's what defines it at 25 degrees. Away from 25 degrees, this number changes. It's not 1 times 10 to the negative 14th, which means neutral is no longer 7, because neutral is no longer going to be 10 to the negative 7th molar H+. Does that make sense? Make sure that you tuck that away and make sure that does make sense to you, okay? And obviously in a basic solution, there is more hydroxide than hydronium, and acidic means more hydronium than hydroxide, right? And always make sure you take 2 seconds and read over your written answer and make sure that you've reasoned through that correctly, because I don't know how many times I say the wrong word, but I mean the right word. But obviously on a written test, like, I don't know, like say that whole AP exam thing you're going to do, right? That you can't get the point, right, if your words don't match, right? Does that make sense? So, just be thoughtful and double check. All right, pH scale, this is the exact same as it was last year, right? Wherein pH is equal to the negative log, right, of our hydronium ion concentration, right? pOH is always going to be the negative log of our hydroxide ion concentration, right? And pOH plus pH is equal to 14, right? Which is based on the fact that our H3O plus times my OH minus, right, is equal to 1 times 10 to the negative 14th, right? Which log properties gives us that. Yes, does that make sense? Okay. Make sure you know those equations and you can manipulate them. Here, this is kind of like that figure we looked at last year, right? Wherein we get a pH and a pOH of 7 when my respective concentrations are 10 to the negative 7th, right? And that's what gives us our hypothetically pure water, right? And then obviously as we change those, right, so if we go over here to something that is very acidic, right, we end up with a pH of 1, which corresponds to a H plus concentration of 1, right? 13 of a pOH corresponds to a OH concentration of 10 to the negative 13, right? Meaning that there is very little hydroxide relative to lots of hydronium, right? Which gives us a very acidic pH, right? Whereas if we come to the opposite end, right, we see the opposite scenario where we have 10 to the negative 13th for hydronium, which leads to a pH of 13, right? pOH of 1, 10 to the negative 1 for hydroxide, right? So just be mindful here that we are reasoning through and thinking, right? Because all of the hydroxide ones are one extra step if we're trying to get from hydroxide ion concentration to pH. So just make sure you reason through your answer, right? Like if you get a pH of 13, or you think you got a pH of 13, but it's an acid solution, right? You might want to go back and, double check that you did it all right, because it might be that you just forgot to do a step somewhere in terms of relating pH and pOH correctly, which is the beauty of being able to double check in chemistry, right? All right, so make sure you understand this, make sure it makes sense to you. Okay. Last up, measuring pH, right? The few of the methods that we have available, right, are one, using a pH meter, which hopefully if time and conditions allow, we will have time to use that, right? Ours doesn't look quite like that, but it's the same principle, right? Where we have a probe, right? Which is basically just a fancy electrode, right? That just basically measures the amount of H plus in the solution via an electrical current, right? Which it then converts into a pH, right? In addition, we have indicators, right? Which we've used previously, but indicators, and the neat thing about indicators, and the reason that they change color is because indicators are themselves weak acids, yes, or weak bases, right? But they're weak acids, right? Which means that they have a protonated form and a deprotonated form, and those two forms have different colors, yes? Or we could say that they have their acid form and then their conjugate base form, right? Does that make sense, right? Protonated and deprotonated, or their acid versus conjugate base forms, and those different forms have different colors, right? And when we look at those different colors, right, they can give us information about what the pH of my solution is, right? So for example, phenolphthalein, right, we have obviously at a pH, a relatively low pH, we have something that is colorless, right? And eventually we have something that is pink, and somewhere in between, we have a little bit of our colorless molecules and a little bit of our pink molecules, and that's why we get pale pink. Yes, does that make sense, right? Likewise for bromo blue, right, we have yellow, we have blue, but if we have a mix of yellow and blue, we end up at green, yes? Does that make sense? Meaning we have some of both species. There is not a third species that is green. Does that make sense, right? Likewise, up here with methyl red, right, we have something that is decidedly yellow, we have something that is decidedly pink, right? And then we have the stages of colors in between there, right? So make sure we're clear on that. That's not true for all of them. Like, so some of them, like this thymol blue, does have three, right? It's got a red version, a yellow version, and a blue, right? And so that's very unique and different, right? But if we're just talking about the color transition between two colors, right? Note that there's not a green version of bromo blue, right? That's what happens when we have some yellow and some blue together, right? Which is why if you think back to our titrations from chapter 4, we were shooting for something that was a super pale pink, right? Ideally a fleeting pale pink, because that would give us something of a pH less than 9 even, right? Does that make sense? Hello, AP Chemistry, and welcome to 16.5, Strong Acids and Strong Bases. So this is exactly what we talked about last year, right? So we will use only forward arrows because strong acids and strong bases are what? Right, they are strong electrolytes, they dissociate completely. And since we're talking about aqueous solutions of them, right, they are already dissolved, right? So we could write aqueous down here if I was being super thorough, right? And we would get our H3O plus, right, and our I minus, right? Here we would get our Na plus and our OH minus. For strong bases, writing it with water gets a little bit weird and confusing, actually. If this were just aqueous, that would be fine. All right. Okay, so then if we wanted to calculate the pH for any of these, right, this is all we need to know, yes? In that whatever the concentration of HI is, right, so let's say this is 2 molar, right, then clearly we now have 2 molar hydronium, which we could then calculate the pH of, yes? Or if we had 2 molar NaOH, right, we now have 2 molar hydroxide ion, which we would then use to calculate pOH and then subsequently pH, depending on what method we wanted to use. Yes? Does that make sense? Do be mindful that sometimes you will find yourself coming up with a negative pH, right? Which you should find makes total sense, yes? Because if we have a 1 molar concentration of a strong acid, right? And if we think about that means, right? Negative log of 1 equals our pH, right? Which if we think about this, 10 to the what is going to give us 1. Correct, right? 0. That means my pH equals 0. So to say that again, right? 10 to the what power is going to give us 1, and the answer is 0, which means that for any acid concentration higher than 1, absolutely we will get a negative pH, and that is fine. Rare, but fine, because we don't often deal with concentrations that high, right? Except like, you know, that when we did that lab where we tried to dissolve the silver alloy, for example, right? But we don't often deal with very high concentrations because they get to be pretty dangerous and hard to work with. All right, for our purposes anyway. All right, thank you for listening. Be good, and I will see you soon. Bye. Oh, by the way, I'm just assuming you can do all these strong acid, strong base pH calculations. If you run into trouble with any of them, please make sure you mark them and come by so we can talk about them, because obviously that is the foundation for all the rest of the weird math we're going to do for the rest of the unit. All right, thanks for listening. Be good.